All right. Hello, everyone. Welcome to a very special colloquium. I am Sid Srinivasa. I happen to share a name with the speaker today. I want to introduce the speaker by first saying something that Dieter mentioned at one of our robotics channels, which is Sid is one of the top roboticists out here. But you already know that about me. So I should introduce. That was my Sid joke, sorry. But I'm sorry. In addition to sharing a name, we also share an academic lineage. So Sid Karamchetty is my academic great-grandchild, my student's student. And so it's a real pleasure to have him here. Sid's from Stanford, advised by Dorsa Sadig and Percy Liang. He's done some really remarkable work in human-robot interaction, robotics, natural language processing, and not just in each of these individual fields, but also at their intersection, which we all strongly believe is critical for us to advance science and for us to advance robotics. So Sid will be giving a talk now. I'd request you ask very few clarifying questions. We'll have plenty of time for full questions later on, but without further ado, Sid.
Great. All right, can folks hear me? All right. Thanks, Sid, for the great introduction. All right. Good afternoon. My name is Siddharth Karamchetty, and I am really excited to share my work towards building and deploying interactive robots to work alongside us in the real world. Now, I want to start by channeling my inner comic book nerd and turn back the clock to 2008 with a scene from the very first Iron Man movie, a scene where Tony Stark, Iron Man himself, is working with his collaborative robot arm to construct what will ultimately become the first version of the Iron Man armor. Now, I want you all to pay attention to what Tony says, how the robot responds, and where Tony's focus is throughout the clip. Now, this was, and still is, the picture that I have in my head when I think about human-robot collaboration. And yet, almost 20 years later, despite so much incredible progress in robotics and machine learning, I'd bet that most of us don't have systems like this in our research labs, let alone our workshops or our homes. Why not? What would it take to build a system like this? Well, let's run it back and take a look at what Tony says and what a robot needs to do under the hood. Up first are these instructions that are explicit, moving closer, or planning a path down to the table. To execute on these instructions, we need robots that are capable of embodied perception, an ability to understand and make connections about the visual world, and then use this understanding to inform action. But then there are things that Tony says that require more than just a literal interpretation. Right? Next requires an understanding that we're trying to assemble this new mechanism. We just finished soldering one connection and now need to move on to the one below. The exclamation, "don't even move," isn't a literal stop moving or else, but more like a, okay, get out of the way, but also please avoid the hot soldering iron and don't burn the workshop to the ground. Now, acting on these instructions requires some extra knowledge about the world, some knowledge necessary for a robot to reason more deeply about its behavior. Taken together, these interactions fulfill a principle that I'm going to call capability, the fundamental tools a robot needs prior to being deployed. Now, I want to make these categories more concrete and highlight some of the problems that I've tackled in my research. Now, let's consider this desk as a simpler version of Tony's workshop and focus on what it means to build a visual understanding of an environment. Crucially, there are different levels of visual understanding. Now, at the low level, it's a scan of the scene, separating parts from the table, getting a rough sense of textures and shapes. At the high level, it's mapping elements of the image to names and meaningful concepts, right? Like this thing here is a 9-volt battery. That thing on the right is a soldering iron. And while ideally we'd be able to capture this full spectrum, prior approaches only tend to capture one of the two extremes. Instead, my early research proposed Voltron, an approach that uses language as a way to bridge these different levels. Let's say I start with our low-level visual understanding, and I give you a description of the image. What happens? Well, if we can look at lots of these language and image pairs, we can start to iteratively build connections, linking similar bundles of shapes to objects or other concepts mentioned in language. But we can go further. We can also try generating descriptions from the image alone. Descriptions like an electronics workspace for assembling simple LED circuits. Not only does doing this let us link to higher level concepts more explicitly, but it's going to help us build scene level connections that are going to help generalization. Now, the important part here is that we're deeply weaving language into how we encode images, really modeling the nuance of how words and individual parts of an image interact, letting us build this robust understanding of new scenes. Now, building from this, we also want robots that can tap into other sources of knowledge to reason and plan. Now, one example from the video is common sense reasoning, avoiding the hot soldering iron. But for this application, we might want more, like asking our robot to identify the 1,000-ohm resistor from this close-up, a question that requires some background information about how to decode resistor values from the sequence of color bands on each part. Now, one way to enable this is with visually conditioned language models, or VLMs, one of the advancements of the past few years that I'm particularly excited about. Now, a VLM is going to take as input an image and text prompt and generate a text response. The model shown here, Lava, is one of the earlier and more popular open source VLMs that came out in early 2023. And it's going to be trained by fine-tuning end-to-end on image prompt response triples. The really surprising part with these models is how efficient they are. With less than 500,000 examples and only about 12 hours of training, we can learn VLMs that generalize far beyond the scope of their fine-tuning data, handling new objects, scenes, and even text prompts with ease. Now, while this seems compelling, I don't want to forget the broader context. Machine learning as a field, 2023 and especially now, is characterized by rapid and unpredictable progress. New models are released daily, if not hourly, each showing tremendous ability, but only capturing the narrowest slice of the broader design space. This makes it hard for us to build intuition about how we might change a model recipe for a new scenario. Now, for Lava, this is maybe a bit more obvious if we peek under the hood. The language model they built from was the 13 billion parameter Vicuña 1.5. And the bulk of images they trained on came from MS Coco, a collection of images from Flickr. I'm not actually sure how many folks in the room are old enough to remember that website. Sourced prior to 2014. And now looking at this, there are different questions people might have. Now, as a roboticist trying to run a VLM in a real-time setting, how small of a language model can I get away with? Do I really need all 13 billion parameters? If I'm trying to process COVID-19 tests, something that didn't exist in 2014, how much new data do I need? To answer questions like these, we developed Prismatic, a toolkit for systematically mapping out and exploring the different VLM design axes. To start, we first assembled an evaluation suite comprised of a dozen established vision language tasks to measure things like general question answering, detection, and even more targeted skills like diagram understanding. We then use these evaluations to contextualize one-step controlled ablation experiments. For example, swapping the 13 billion parameter Vicuña model with its 7 billion parameter variant, or even going a step further and seeing if just extending train time with a smaller model, just adding a fixed upfront cost, changes results. Now, running this investigation and distilling the impact of the different design choices really mattered and was key in letting us train state-of-the-art VLMs. This graph shows our flagship VLM, Prism 7B, significantly outperforming the base Lava models given the exact same data and compute budget. But the most important takeaway from our study was that our empirical understanding of the individual changes, each intervention like doubling the number of train steps, that understanding seems to transfer better across different VLM families. This is especially important as we're interfacing with the broader ecosystem of VLMs that are open weights but maybe trained on proprietary data, or even those that are served through restrictive black box APIs. All right, if capability captures the expectations I have of my robots prior to deployment, then the next principle needs to capture what happens after, actually putting the robots in the world with real people. Now, returning to the video, there are things that Tony does that start to hint at a level of fluidity, a sort of flow state he'll hit with the robot. He'll physically stop it, expecting it to back away. Or he'll use his voice, pausing and emphasizing to modulate its behavior. Handling these types of multimodal interactions online during deployment feels like another important part of the story. But to me, the most powerful parts of the video are when Tony uses these interactions as a springboard for teaching new concepts and behaviors on the fly, expecting the robot to correct and extrapolate from his feedback in real time. Now, taken together, these two pillars fulfill a separate principle I call sustainability, building robots that adapt and grow during deployment through natural interactions with people. Now, to drive this home, I want to return to the question I asked at the start, right? How we might build a system like this today, a system that enables these types of fluid interactions and real-time teaching. Now, one caveat, I don't actually know how to build an Iron Man suit. I also definitely don't have the IRB approval to do so, but I do have another very nerdy hobby that might help us split the difference. That being stop motion animation. All right, so for the uninitiated, stop motion is a filmmaking technique where a director, me, is going to incrementally change and photograph a scene to capture the illusion of motion. Now, while this example is relatively simple, with a stationary camera, you can consider shooting more dynamic motions, like orbiting around a character or tracking them as they move. Motions that require reliable and precise camera control. Now, I have shaky hands, making this pretty hard for me. but maybe it's the sort of thing a robot would be good at. Which brings me to Vocal Sandbox. Here, you're going to see my co-lead Jen working with the robot over the course of a continuous, uninterrupted 2-hour period to shoot a stop-motion film, shown on the top right. Now, the goal with Vocal Sandbox is to combine the models we built under capability, our perception models and VLMs, and build robots that grow more capable over time through natural interactions with their partner. For example, we want to allow users to teach new objects like the big Avengers logo with just a simple gesture, or motions like how to orbit around a character just from a single demonstration. The challenge here is generalization, figuring out how to use this feedback to learn concepts and behaviors we can access later on. For example, we might want to understand the A icon and big Avengers logo refer to the same object, or understand that orbiting is a motion that's defined relative to a specific character. Here, the vocal in Vocal Sandbox is going to do the heavy lifting. Language is going to act as a bridge, one that's going to take the different types of feedback and lift them up into reusable building blocks. Think programmatic functions and arguments, things that we can chain together and interpret. The result is a collaborative robot that not only grows more useful, but one that does so reliably. All right, in the rest of the talk, I want to dive more deeply into the different projects I highlighted. I'm going to start with capability and expand on our approach Voltron for learning these multi-resolution visual representations with language. I'm then going to jump into Prismatic, investigating the design space of VLMs, as well as some follow-up work on building vision language action models for robotic control. Crossing over to sustainability, I want to expand on Vocal Sandbox and highlight the role of language for building robots that can adapt and generalize from real-time feedback. And then finally, I'm going to briefly zoom out to discuss my broader research agenda, as well as some directions for future work. OK, great. Now, I want to start by returning to our visual understanding example from before and formalize the setting. Now, our goal is to learn a model that maps an image to a set of vectors that encode what I'm going to call useful features of a scene. And the hope is that by pre-training this encoder on large, diverse data, we can enable efficient transfer, using our representations as a starting point to fine-tune for specific downstream tasks. In this case, learning a vision model control policy from a relatively small number of demonstrations. Now, because we care about embodied perception, especially for robotic manipulation, we're going to be pre-training our representations on something v2, a moderately sized data set comprised of people manipulating common household objects, literally doing some verb with some noun. Now, earlier, we defined different levels of visual understanding. I want to make this more crisp by highlighting concrete applications that exist at different points along the spectrum. Starting at the low level, in warehouse packing applications, we want features that are useful for things like low-level graph segmentation. In more free-form manipulation settings, we rely heavily on models that can understand objects as well as their affordances. And for broader HRI applications, like in assistive feeding, we want to capture higher-level properties of entire scenes. What are people doing? How are things changing over time? And so multi-resolution representations, kind of like a camera that has different levels of optical zoom, are those that capture the full spectrum of these features. And unfortunately, prior approaches fail to capture this, instead defaulting to one of the two extremes. Now, on the one hand, we have approaches like masked autoencoders that are going to learn representations through reconstruction, basically erase part of an image and learn to reconstruct the missing pixels. This is going to encourage local pattern recognition and capture properties like texture and shape. But looking at this image, there's more going on, right? A person is peeling something in a kitchen with a ton of other vegetables and kitchenware around. This feels like important global information we want to encode. Now, other approaches favor these higher level semantics. Approaches like OpenAI's Clip that learns to match images with their captions. Now, these lie at the other extreme. They're going to encourage representations that focus on high signal bits, things like objects and other things that are easily described in language. For example, Clip representations of these two images are treated similarly because in both, someone's holding a carrot. But now we have the opposite problem, right? Focusing on the high signal bits erases the important local information. Now, as a result, we find that this image of a dog is also treated similarly to our starting image, right? Someone's still technically holding a carrot. Instead, our key insight is that we can use language to bridge the feature gap. Specifically, we're going to craft an objective that balances conditional image reconstruction and language generation. To provide some intuition, and I think this is really important, I want you all to consider reconstructing this image and think about what you're spending model capacity on. Right? There's some orange object in the middle of the scene and maybe some semblance of what looks like a hand. To generate the missing pixels, we're basically asking our models to consider the whole space of possible orange things that might appear in someone's hand, which feels really, really hard. But now let's say I tell you that we're peeling a carrot over a counter. What changes? Well, I can collapse that orange object to a caret and just like knock that out. Similarly, if I'm peeling something, I kind of know what the rest of the hand should look like. Similarly, if I've seen enough kitchen counters, I can fill in the right side of the image. In other words, language conditioning is going to do two things. First, it's going to let us tie words and phrases to individual parts of an image. And second, it's going to let us shift model capacity to the harder parts of the image, finer-grained features like the exact positioning of objects relative to each other in the scene. Now let's move to language generation. Given just the image, try to generate each word in the caption one at a time. Now this part of the objective is going to let us link to higher level concepts more explicitly, in a way that's going to strengthen connections at the scene level. It's also going to facilitate strong generalization, linking these features to similar contexts across my dataset. Now this simple objective, using language conditioning and generation together, is the backbone of our approach. Now implementing our framework, Voltron, is straightforward. We're going to start with a multi-frame masked autoencoder. Again, this is going to be our starting point to learn low-level features. And for the first part of our objective, we're simply just going to let our model attend to the words peeling a carrot as we're encoding the masked images. We're then going to extend our model with an autoregressive language decoder, right, using our learned representations to generate the corresponding utterance. Now note that we can't condition and generate simultaneously, or we'd be leaking information. So instead, we're going to set a hyperparameter alpha that acts as a sort of biased coin. For each example in our data set, we're going to flip this coin and either condition or generate based on the outcome. Now after pre-training, we're going to use our representations to help kickstart fine-tuning, using them as building blocks for downstream learning. Note, however, that we get a little something extra from our model. Because we train with language conditioning, we can provide multimodal representations that learn to pre-mix language and image features together. This is going to be especially important in a little bit. Now, we evaluate our learned representations on a range of applications requiring different blends of these visual features, from the examples on the earlier slide to other tasks like modeling in a person's intent over time. And crucially, we show that Voltron representations not only uniformly outperform prior approaches across the board, but they do so by training on much less data, which is a huge win for efficiency. I want to highlight one of our more significant experiments, evaluating Voltron representations on object detection from referring expressions. Now, the evaluation data set we use is called OCID-Ref, and it's nice because it's split into scenes with different amounts of clutter to test model robustness. Now, I particularly want to call attention to the strong performance of Voltron relative to CLIP and masked autoencoders, and talk a little bit more about data efficiency. Right? Voltron is outperforming models trained on 2 to 3 orders of magnitude more images. Right? Again, it was only trained on 500,000 images from something v2, while CLIP was trained on over 400 million images from the internet. The primary reason for these gains is that we're starting from these multimodal representations that I highlighted earlier, representations that have already captured how images and text interact. This isn't the case for the prior approaches. For example, in CLIP's case, we're treating language really as a label, learning 2 completely separate models, one for representing images and one for representing text. Now, this idea, being intentional about how we incorporate language during learning, is one of the key takeaways of this work, and is a general point that I think extends far beyond representation learning.
Clarification question. Since I made the rules, I can ask this.
Sure.
Are there multiple language representations for a single image, or is it one-on-one?
So it is a set of representations for each token in the corresponding utterance.
Like here I could say it peels the carrot. Or
Yeah, so you basically get like the corresponding word embeddings process.
So, maybe I can also describe it as like stands in front of a plate.
Mm-hmm.
So I can do all of that.
Yeah.
And then I guess like how rich is that? Like does that matter? Like in your training data set,
Mm-hmm.
like how do you create the, like how much should I believe in that textual representation?
So the text representation by itself, right, because it's like we're not really supervising it with the Voltron objective anywhere. It's just kind of as part of the training process. Using it alone, kind of with the model as is, isn't super helpful. The real impact is when we just start adapting for downstream tasks, right? Then you're kind of able to kind of leverage that information, especially kind of in that detection task from language that I just showed. Okay. Now, in this next part of the talk, I want to build on the principle of capability we defined earlier and work towards learning models that can incorporate other sources of knowledge to reason and act in the world. Now, I want to start by returning to our schematic of lava. Now, recall that the key idea with a VLM is to map images, or more specifically, these image representations into the input space of a pre-trained language model. We're then going to fine-tune on a fairly small data set of image prompt response triples, resulting in a model that can answer questions, chat, or otherwise reason about images. Now, like I mentioned before, each new model only tends to capture one set of design choices, which makes it hard for us as researchers and engineers to build intuition for how to change or tweak a model for new scenarios. Now, I want to dig into some of the design choices that Lava made to help us start to ask questions and map out the different design axes that might matter in building VLMs more generally. Now, the language model they chose to build from was the 13 billion parameter Vicuña 1.5. This is a chat-tuned model that's derived from Meta's Llama 2. Now, we asked this question earlier, but why 13 billion parameters? Could I have gotten away with a smaller model? Also, why use a chat-tuned model instead of a base language model? The image encoder used in the initial work was CLIP, which should start to immediately raise some red flags given what we just learned with Voltron. What about reasoning requiring a finer-grained understanding of scenes? Going a level deeper, and I will literally die on this hill, I want to talk about the image preprocessing scheme used. So I could go on about this for hours, but the important detail here is that most image models require square inputs at a fixed resolution. If your image isn't square, and most images aren't, right? This slide is 16 by 9. Your phone's going to shoot anywhere from 4 to 3 to super ultra wide. The default approach they used in the original work was to resize the image to the appropriate scale and just chop off either side until it's square, literally losing information. Feels wrong. Now, there are also more nuanced questions we can ask about how the model scales. Questions like how performance scales as we add data, or if we just simply increase training time. Now, asking these questions allowed us to codify the different design axes in building VLMs and let us build Prismatic, a toolkit for systematically exploring the design space of these models. We came up with 4 key axes and populated our initial experiments following the questions I asked on the previous slide. Now, while the primary contribution of this work was the study itself, right, ablating the various design choices, doing the one-step controlled experiments, I really want to highlight Prismatic as a resource contribution. We built one of the most hackable open source code bases for training different VLMs, one that can easily assimilate new model components and data sets as they become available. This data class, this Python object that you see on the right, is literally how we configure VLM training in our code. As you can see, every one of the different design axes is made fully transparent to users. Now, in addition to our training code base, we also assembled a comprehensive evaluation suite composed of standard tasks from the last decade and a half of vision language literature to isolate and calibrate the impact of individual model changes. The first set of tasks targeted general visual reasoning from tasks like VQA v2 to tasks like text VQA, which actually requires reading the text in an image. For example, reading the sign to get the price of bananas per kilogram. We also included more targeted localization tasks. Here, OCID-Ref appears again for robotic settings, but we also include the different RefCoco tasks. Here, what's really cool is that we're literally asking the VLM to generate bounding boxes as structured strings, literally generating the JSON lists you see here as text. Finally, we included challenge tasks to probe things like fine-grained visual reasoning, as well as other higher-level things, like a VLM's propensity to hallucinate when responding. Now, with this combination of our code base and these evaluations, I want to discuss some of our major findings. The first finding we actually flagged as one of our key questions, like why use clip representations? Here, the simple question is what happens if we try fusing different representations that capture both the low-level and high-level features we were talking about, and kind of rely on the language modeling objective, this text prompt and text response, to kind of act like the Voltron objective and help bridge this feature gap. To test this out, we tried combining Dino v2 and SIGLIP features, just by simply concatenating them prior to the projection layer. Here, you can think of Dino v2 as learning representations similar to masked autoencoders, just trained on a much broader set of data. You can similarly think of SIGLIP as basically identical to CLIP, but trained on a broader data set as well. The results are pretty incredible, right? Not only does training with these just concatenated features preserve performance across the board relative to training on the SIGLIP features alone, but especially on fine-grained tasks, right? The RefCoco and OCID-Ref at the bottom of the screen, we're seeing much better performance, like an average increase of over 10% in detection accuracy, just with a simple concatenation-based strategy. Continuing our exploration surfaced a ton of other obvious results. For example, the suboptimality of resizing and cropping, to more nuanced things about how to properly optimize the model to prevent early loss collapse. In all, the biggest findings we had were the use of these fused features to get at fine-grained details, a more optimal image processing scheme. It turns out that you can, depending on the visual representations you use, you can actually get away with just warping the aspect ratio, literally just stretching the images to square without any ill effects. And finally, the importance of co-training on LLM instruction data for safety, preventing toxic or otherwise biased outputs, as well as just slightly oversampling any data requiring generating structured outputs, just to make sure generations conform to the right format. The results again speak for themselves. In a data and model size controlled experiment, we're able to show that we can significantly outperform the base LLaVA models across the board, especially on tasks requiring finer-grained visual reasoning. Now, I want to pop back up and remember our original goal, working towards capability, building models that can incorporate external knowledge when reasoning about the world. To dig into this, I want to show you a few examples of our best VLM, Prism 7b, in action. So this is a picture of my apartment sink with some of my roommates' dishes that I cleaned up a little bit so they weren't like completely gross for today's presentation. Now, in terms of integrating background knowledge, we see that the VLM is able to reason pretty well about objects that are dishwasher safe, namely the knife and the spatula. But it's also able to flag that the frying pan has a non-stick coating, right, like indicated by that Teflon logo in the middle, that needs its special care. The VLM is also capable of fine-grained spatial reasoning, detecting the Yeti mug in the image with high fidelity, even though there's another mug in the sink, and Yeti mug doesn't appear anywhere in the fine-tuning data. Finally, the VLM is even capable of just conditioning on bounding box regions to generate responses, which I just think is just a really cool capability. For example, just being able to like circle an image on an iPad to just ask questions. For just 8 hours of training and a fairly small data set, these results are still mind-blowing to me, and why I'm particularly excited about VLMs moving forward. Now, that being said, there's a question I've sort of been dancing around, which is how we might actually use these models for robotics, especially robotic control. As for why this is even a good idea, I think, again, the historical context matters. Specifically, I want to highlight some challenges with trying to scale robot policy learning with the approaches we were using in mid-2023. Our architectures tended to look like this. Again, echoing this recurring problem we've seen throughout this talk. We're just taking some off-the-shelf image encoder and a separate text encoder and just placing the huge burden on the rest of the model to learn how to weave things together. Furthermore, scaling to larger data sets introduces other issues like unstable training or weird forms of underfitting, issues that seem to stem from the particularly learning objective that these approaches use. Instead, VLMs serve as a pretty great way to mitigate these problems, right? The benefit here, again, echoes Voltron. The whole point of VLM training is that we learn how to effectively weave together vision and text up front. But the big reason why learning policies on top of VLMs is a good idea is because it lets us tap into the last 6 years of progress in language modeling research. Training a model like this is basically identical to training a language model, letting us tap into the full ecosystem of tools and best practices for debugging and deploying these models at scale. Now, Google was one of the first groups to operationalize this idea with their model RT2, albeit for their custom robot platform using proprietary VLMs. Beyond using a VLM as a starting point, the last piece of the puzzle they addressed was how to turn continuous robot actions into text. Now, building off the ability of these models to generate structured outputs, RT2 proposed a pretty naive scheme for quantizing a robot's actions, just mapping the change in pose of a robot arm to a sequence of tokens. And the results were pretty incredible, showing policies that could generalize to different instructions, objects, and behaviors. Results that sort of lit a fire in me to try and build an open source VLA, something that other people could actually use and build on. Now, in trying to fuel this fire, I got lucky, and that the timing worked out to create kind of the perfect storm of data, models, and just an amazing team of collaborators. Now, while open robotics data was historically scarce, Carl, one of my co-leads on OpenVLA, had just finalized OpenX embodiment, a huge initiative building a catalog over 1 million robot demonstrations comprised of data collected by researchers at over 21 institutions spanning 22 different robot embodiments. Coupling this data with our expertise with Prismatic, we were able to train the 7 billion parameter OpenVLA and first show the same types of results as RT2, namely that we could deploy our policy to robot embodiments captured in the OpenX collection and generalize to new scenes and objects and instructions. But more importantly, we expanded on the RT2 results and showed that we could fine-tune VLAs for completely new robot embodiments and tasks with very small data sets. For example, taking only 70 demonstrations to perform the fairly complex sweeping task on the bottom right. Now, I want to be super transparent about limitations here. While these models are data efficient, fine-tuning is still pretty costly from a compute perspective, taking several hours to converge for newer robots. That said, a bunch of follow-up work has been trying to significantly cut this cost, proposing new techniques for things like efficient transfer. Finally, I want to touch on impact. I am incredibly humbled and excited by the different ways people are using and building off of Prismatic and OpenVLA. For Prismatic, our open source code base has has enabled more open science. We continually get PRs from folks in the ML community contributing new VLMs trained with the latest models and data. Here, this is a PR with someone just dropping like 15 different models trained with various different, more modern LLMs as the backbone. Folks have also used our models and toolkit to explore new research directions. For example, using our VLMs to build robots that can actively explore new environments. Similarly, our OpenVLA codebase has gotten almost 2,000 stars in just the 6 months since we published it. Furthermore, if you track downloads through our Hugging Face page, we're seeing an incredible amount of interest in people just trying out our pre-trained models. All right. Now, in this last part of the talk, I want to transition to our second principle, sustainability, and actually use the models we've built so far to develop a real collaborative robotic system. Our goal, again, is to build robots that can adapt and generalize from natural feedback from their partners. And we're really looking at ways to build robots that grow more useful over time, learning completely new concepts and behaviors in a way that enables richer collaboration. To make this concrete and really probe at what it takes to build collaborative robots that are useful for different groups of people, we designed 2 scenarios, or sandboxes, kind of how it gets its name. In the first, we built a controlled gift bag assembly line task. Here, the goal was to engage with non-expert users, folks with minimal ML or robotics expertise, to do a pretty repetitive task of just assembling multiple gift bags packed with the same objects. To encourage collaboration, we also had each user write a pretty lengthy handwritten card to attach to each of the bags. The hope here is that a good collaboration is one where work is parallelized effectively. Now, in the second scenario, which you already saw, we focused on the stop-motion animation setting, using the robot as a sort of controllable camera arm. Here, the goal is to see how far experts, namely me and my co-author Jen, people with insight into the system, with experience working with robots, how they could scale the system for more free-form tasks. Now, one way to design the system, building directly on our results with VLAs, is to just learn a policy from demonstrations in each of the different scenarios and continually fine-tune the model as users try to teach new behaviors. Unfortunately, this isn't as straightforward as it sounds. Here, we've trained a policy for a single task, and we're deploying it in just 2 slightly different scenes. Everything is pretty much the same, except for maybe like the background objects. What do you think is going to happen when I hit play? Well, the robot on the left seems to be doing the right thing, but on the right, kind of completely fails, and it does so like pathologically. This surfaces 2 problems. First, being able to localize and explain failures. After training this policy and watching it fail, I still have really no idea what just happened, right? Like, was it a vision problem or something else? Second is the real-time adaptation component, right? Let's say I wanted to teach different tasks. Like we just mentioned, even our best VLA models needed at least a couple dozen demonstrations and hours of fine-tuning to generalize to these new behaviors. These problems get at a broader question, that of the expectations we have of our collaborative robots. Now, this first expectation is transparency. Let's consider a user in our gift bag assembly line setting. What does this actually mean? Well, given an instruction like, can you grab that jelly sandwich candy thing? It's getting a sense of what the robot plans to do, being provided with an interpretable trace that explicitly links instructions to actions. In this case, it's being shown a segmentation mask of the object the robot intends to interact with. This should also extend to cases where the robot is uncertain. If it doesn't know how to do something, it should be able to vocalize this uncertainty to their partners. The second expectation follows pretty naturally. It's exactly the real-time adaptivity and extrapolation I motivated at the beginning. Right? If the robot doesn't know how to execute a certain behavior, the user should be able to teach it. Right? For example, by decomposing their original instruction into simpler steps, things the robot can understand. Crucially, the robot should be able to generalize from this immediately, as soon as the user provides their next instruction. And I think this should link back to transparency. Right? If the robot knows the behavior to execute, but is missing something lower level, like where to find the green toy car mentioned in language, they should be able to vocalize that uncertainty as well, and ask their partner to provide targeted teaching feedback. In this case, literally showing the robot what object on the workspace they're referring to. Now, to realize these properties, we designed Vocal Sandbox around some ideas like modularity and interpretability. The key idea, though, was to map users' instructions to programs and teach new behaviors and concepts by synthesizing new functions and arguments from different types of feedback. To start, we wrote just a simple Python API for each scenario, comprised of some initial functions, typed argument literals, as well as access to learn models, like the VLMs we built under capability. To execute on a new utterance, we then just feed the new instruction and the API to a powerful language model. In our case, OpenAI's GPT 3.5 Turbo, just having it generate a satisfying program that kind of outlines the plan the robot's going to take. We then feed this plan to the submodules like our VLM. Here, we're just going to try to execute any of the relevant submodule calls, returning as output the interpretable traces I just highlighted. And then finally, we're going to feed the output to our action module. And this is literally going to show the user in simulation the trajectory the robot is going to execute on, ensuring transparency at all points of the collaboration. Now, to teach new behaviors, we're going to synthesize new functions for our APIs by having users decompose their initial instructions into simpler steps. For example, here the user is going to decompose pack into picking up the candy and then dropping it in the gift bag. And after they're done, they're just going to give the robot the all clear, like the thumbs up, to trigger the synthesis step. For synthesis, we're actually going to prompt our language model with the current API and the full conversation history, and just ask it to generate the new function signature. Literally the name, input types, and the doc string that you see here. We're then going to use just some simple lifting heuristics to generate the function body from the predicted type signature, and making sure that we can pack any object, right, instead of just packing the candy in the grounded program during the teaching episode. Teaching at the lower level is going to work in the same way, just synthesizing new arguments instead of functions. For example, when asked to pack the green toy car, we're going to generate as much of the program as we can, but clearly vocalize when a given argument doesn't exist in this API. Then, based on the inferred type of this argument, we're going to ask our partner for targeted teaching feedback. Here, again, we're literally asking the user to show us where the green toy car is in the workspace. This is going to then trigger a similar synthesis step where we add a new typed literal to our API. Using our VLM to come up with a few descriptions we can use to find the object later on in the interaction. Now, what's really cool is that we can teach increasingly expressive behaviors by composing things we've already taught. For example, in this video from our user study, the user has already defined a function for assembling the entire gift bag, building on top of the pack object function he's already taught. This is what his interaction looks like.
Assemble the gift bag.
So notice the graphical interface on the top left. It's going to highlight the interpretable traces output by a robot along the way in real time. Now, additionally, as the user works on writing their handwritten card, the robot's going to periodically ask him for confirmation that it's doing the right thing, just requiring him to briefly glance up and just provide spoken confirmation. Now, we evaluate this variant of our system through a long horizon user study with 8 subjects, each spending 3 hours with the robot for this task of assembling 4 gift bags in a row. And our results show that Vocal Sandbox systems are not only useful, but reliable as well. To contextualize our results, we compare against 2 baselines: a system that only has access to the initial API, so basically no teaching, and a separate variant of our system that removes the structured modularity of our system, instead letting the language model kind of go wild and synthesize new functions and arguments on its own. First, we find that over the course of the task, users are defining and using more complex behaviors, functions like assemble gift bag that break down to longer chains of the base API functions. More importantly, we find that users qualitatively prefer working with Vocal Sandbox systems relative to the baselines. I especially want to highlight the rankings assigned for predictability and helpfulness here. Finally, we looked at collaboration efficiency. For the 4th user in our study, we see that early on, a lot of the time up front is spent instructing and teaching. But by bags 3 and 4, the user spends most of their time focused on writing the handwritten card, letting the robot handle the actual packing behavior, effectively parallelizing and collaborating. Now, looking forward, I'm really excited about the broader impact we're already starting to see with Vocal Sandbox. As we speak, we're actually in talks with different establishments in the Bay Area to actually use our Vocal Sandbox systems to help with time-intensive and unstructured tasks, things like portioning dough or measuring out ingredients. What I'm particularly thrilled about is that we're actually building up a paradigm for what I'm calling forward deployed robotics, one where we're actually shadowing employees at these different establishments, getting a sense of needs, and iterating on robot skills on site. We're also starting to figure out the right way to provide people with system tutorials, showing how they can grow and adapt the system completely on their own without any experts in the loop whatsoever. All right. In the last few minutes, I want to zoom out and touch on my broader research agenda and highlight some different directions for future work. Now, the central theme of my research revolves around being intentional about the role of language in robotics, especially as it relates to building robots that can learn from and work with people. I think this is really the foundation of the 2 principles I've been using throughout this talk. Under capability, we already talked about my work in learning for perception and control. What we didn't get to talk about is my work on data curation and analysis, really trying to get at what truly matters when we're collecting data for robot learning and embodied understanding. Now, one example of this is my work on the DROI dataset, a dataset of 90,000 robot demonstrations collected on a common platform spanning 12 institutions across the world. Now, under sustainability, we covered some of my work building adaptive systems for collaborative robotics. But I've also worked on more traditional human-robot interaction problems, looking at ways to reduce friction when working with robots. For example, building robots that are more proactive in turn-taking settings, and even designing new interfaces for applications in assistive robotics. Now, in terms of future work, building on capability, one direction I'm excited about is pushing towards more dynamic and complex manipulation. If we look at the current tasks we're indexing on in robot learning, we're seeing an emphasis on tasks like these that focus on semantic manipulation, manipulation in mostly static scenes, tasks where images and text are really enough to predict the action the robot needs to take. Instead, I want to tackle more complex applications that I'm pretty passionate about, things like in assistive caregiving and household robotics, applications where this assumption really starts to break down. Here, control needs to be more reactive, and behavior depends a lot on the information that are coming from other sensor modalities, kind of like the force exerted on an object or tactile impressions. Now, one challenge is how to integrate these custom sensors, especially given limited data. Now, my mental model here is to decouple what to do from how to do it, right? Leveraging vision and language for the former, but learning specialist policies for actually synthesizing actions. Another challenge is looking at ways to integrate external models, tapping into simulation and recent progress from the 3D vision community to do things like generate a mesh from just an image of a novel object, load it into simulation, and search over it to find a new grasp. Now, building on sustainability, I really want to reconcile current methods for policy learning with the ideas of adaptivity and transparency in Vocal Sandbox. Let's consider this long horizon task of setting a table, a task where there are tons of different points of failure and ambiguity. Even if I had access to a ton of data, expecting perfection from a learned policy kind of feels out of reach. Instead, I want to build in ways for people to intervene during deployment, either in person or remotely. For example, just pointing at or using an iPad to circle the mug I want the robot to interact with early on in the interaction, or later, providing a language correction, kind of like plate by the dish rack, or even scribbling out parts of the scene that I want the robot to avoid. We can then use these interventions to condition what I'd call an interactive VLA, converting feedback to text or images as appropriate. Here, adaptivity is then a function of learning to condition on these interventions in real time. By default, switching all of our policies to be semi-autonomous by default, basically always ready to take on human interventions. Longer term, we can get at transparency by prompting our model to generate traces ahead of their actions. Eventually, we might actually want to explicitly verify these traces for things like safety or kinematic feasibility. Ultimately, I hope that we can start finding real-world domains where these policies can start providing utility so that we can actually engage with real people, naturally working our way towards building broadly capable and reliable robots. Okay, I want to end where we started. At the very beginning of this talk, I asked you to track where Tony's focus was during that original Iron Man clip. I didn't really say much about it at the time, but that for the bulk of that interaction, he wasn't ever really focused on the robot. Instead, his eyes were glued to the work in front of him, assembling that piece of armor, kind of really just trusting and relying on the robot to follow his lead. I want to contrast this image with how we deploy and what we expect of our robots today. We put them in factories, designing our environments around them, throwing up huge sheets of glass to silo them off from real people. Even in more human-robot interaction settings, we're never really deploying them for longer than a few hours at a time. And always with a couple people in the room watching carefully, clutching at the emergency stop just in case things go wrong. If there's anything that I want you to remember from this talk, it's that we need to break beyond the status quo and instead work our way here to this picture. A world where robots are as useful as they are ubiquitous, and where trust and reliability is the rule and not the exception. And I'm going to be honest, I don't know how long it's going to take for us to get here, be it 5 years, 10, or the rest of my career. But I'm absolutely certain that this is the future I'm going to work towards, a future where robots disappear. Thank you. Happy to take questions.
All right, we have time for questions. Ask away. We have microphones here that will capture your voice for the folks on the video stream.
Yeah, please hit me with the hard stuff.
Abhishek.
I guess there was So I think there's a different set of methods in part 1 and 2, and 3 was more modular. But it felt like you're kind of trading off capability and interpretability. Like, how do you, like, are there ways to get the best of the capability you saw in 1 and 2 while retaining interpretability? Like, how does that?
Yeah, so I wish this weren't the case, but I think right now with the methods that we have, there is this trade-off between the expressivity of the types of behaviors we can learn and the interpretability, verifiability of them. With this kind of adaptive, transparent, like policy learning angle that I just talked about, I think we can maybe start to move away from this, but I really do think it's something that we need to be more intentional about as we kind of train these policies. And it's something that I'm really excited about, like looking at moving forward. I do think this idea of kind of generating these traces ahead of time is maybe one way to get at this, especially if we can figure out ways to explicitly verify them.
Go ahead.
Very technical question about like the first of the three which you mentioned about training the VLM.
Mm-hmm.
You said that your method's like much more data efficient. So just to be sure, so when you trained your model, did you use any like did you use did you fine tune some base model at all? Or you really just like the 500K, you know, just that's the only data that's ever used, and like you start from random initialization or whatever?
No. So like I mentioned in the part of the talk, we're starting from a pre-trained language model and some pre-trained image representation. So like SIGLIP or CLIP representations, and a language model like Llama 2 or Vicuña. And then we're just fine-tuning through that entire pipeline with those 500,000 examples.
I see. And the claim is that the other things, if you want to fine-tune them, you need much more data as well?
No. So the claim with the VLM part of the talk was mostly about the exploration through VLM design space, right? Really kind of like figuring out like, okay, what's the right way to incorporate these different image representations? You know, how big of a language model do we need? What's the impact of different types of representations on different evaluation results, right? So they're all kind of controlled experiments starting from this point of a pre-trained language model, some pre-trained image representations, and maybe a fixed data set to kind of help bridge the gap. And then in the final experiments that I showed, we kind of show that like given kind of the same data and compute budget as the base LLaVA models, the models that I was talking about kind of from the beginning, we're able to get significantly better results just by making some smarter choices about the individual components.
But I guess the thing about like data set size is a little bit unfair then, or something. I guess I don't fully understand the comparison about data set size.
So LLaVA and the prismatic models and the results that I flashed up were trained on the exact same data with the exact same model capacity, right? So the LLMs were the same size, so the same rough parameter count. Data was the same size. What we just added were things like swapping out the image representations from the basic CLIP to kind of the Dino SIGLIP representations. And similarly, swapping out the image preprocessing scheme to that aspect ratio warping scheme.
Steve?
Super cool. I was wondering, you know, some of your examples, you know, are really kind of addressing like on-purpose toy toy problems, like literally toys, which is cool. But I mean, when do you think that, you know, this will get to a state where it's like useful and for what kinds of problems?
So a huge part of the type of research that I want to lead kind of as a faculty member are trying to look at actual applications in things like assistive robotics, elder care. Now, the hard part with those problems, kind of just beyond, I think, actually like figuring out the right set of participants and applications, is that we need to find situations and places where people are kind of okay with the fallibility of robot systems, right? The key part of the vocal sandbox part of this talk, kind of where a lot of these toy examples showed up, is that like at no point are we really expecting the robots to be perfect, but we're kind of using the structured modularity kind of ensure that there's always a path to eventually getting to success. That does mean the robot is still going to fail sometimes. And for kind of higher stakes applications that are away from these toy examples, that tolerance for failure might be completely different. So one of the things I'm really excited that I kind of hinted at with the broader impact of the vocal sandbox work is trying to find more applications in the real world. So like the bakery cafe settings where we're kind of measuring ingredients, where like maybe the occasional mess up is okay. And like using that to kind of pave our way to more and more complex tasks as we kind of work on improving the capabilities of our existing systems.
Even the bakery scenario, I mean, robot might cost like $100,000 or much more than that, right? Is that really feasible?
Well, I mean, so the robots that we're actually deploying are kind of these low-cost robot manipulators, actually mostly on a stationary base. It's like $3,000. And they're things that we're kind of providing and like hosting for them. And it's all about trying to kind of balance this idea of like utility provided versus like the upfront cost. And so part of this kind of forward deployed robotics paradigm where we're actually like going in and shadowing the employees and talking with them is trying to find kind of that right trade-off in cost and capability.
Right.
I was wondering if you can talk a bit about the lessons you learned while creating OpenX, Droid, and subsequently OpenVLA. What worked, what didn't work? These were gigantic sort of efforts bringing together multiple institutions.
Yeah.
What kind of data is still missing? How do we get to these general purpose VLAs? Or is this modular approach, like we mentioned in the third part, really where we should be going instead?
Yeah, so it's a great question. So I'm going to talk about Droid specifically. So kind of key idea with Droid was we kind of called up like the whole family of robot learning researchers across like a bunch of institutions worldwide, and especially like came together as a community to kind of like start with just focusing on a fixed robot platform, right? A Panda arm on a standing desk. From there, what we basically did was we said, okay, let's also like kind of settle on the sensors involved. So we kind of fixed like 3 stereo cameras, 2 external, 1 on the wrist. And then, as a sanity check, we basically had each lab just collect like 200 demonstrations of a single task, a pen in cup, just placing a pen on a table into a cup. Now, after that point, we basically just said, okay, we want to maximize the diversity of this data set. So go out, all of the PhD students, all of the folks at these different labs, please go out and just collect as much data in whatever environments, in your homes, in your labs, for whatever tasks you care about. And we actually designed like a graphical interface that like every 5 minutes would tell you to do something like completely change the camera positions or completely change the task that you're executing kind of on the fly. Now, as a result, we had a huge data set of demonstrations, right, 90,000 of them. But for any given task, for any given workspace, we probably had no more than like 5 or 10 actual examples in that fixed setting. And at least when we were trying to learn policies from that data, we weren't too successful just because that kind of scale diversity like trade-off just wasn't there, right? Like maybe this paradigm could have worked, this paradigm of scaling diversity, if we had collected maybe 9 million or 90 million trajectories. But at least at the 90,000 trajectory scale, we weren't getting good results. Instead, what we were able to show was that co-training on Droid data with a given task in mind, like with high quality demonstration data for that task, that maybe improved robustness. So in terms of Droid, in terms of scaling these models, I think one of the lessons we learned with data quality and data curation is being more intentional about the tasks and the way we're kind of growing the capability set, kind of the set of things that we want our robots to do. Right? So I think for me, the lesson was really kind of starting with a narrow task and like building towards more ecologically valid or natural curriculums, right? Like maybe, I don't know, unloading plates from a dishwasher, then unloading mugs, then maybe moving dishes from the sink into the dishwasher, and kind of doing other things with the cabinets, kind of solving the kitchen first, then the rest of the house, then the garage, then the office, then the workshop, rather than kind of like trying to solve everything all at once. And with OpenVLA, I think it's very similar, right? Like OpenX as a subset included Droid, but again, it's capturing basically like PhD student effort from robotic students over like the last 6 years, right? Every data set that folks are collecting for their different papers and just kind of bringing them all together. So again, the mixtures and like the representations of different robot embodiments and tasks were very, very different. Trying to train on all of that was really hard. So actually, if you probe kind of like the very first layer of OpenVLA, like of the image encoder in OpenVLA, like after it's been trained, and you just run a PCA, you can like basically completely linear separate like each of the different data set components up front, right? And that's basically like indicative that you're learning different subspaces for like each of the different slices that we trained on. So we're not in that interpolation regime.
Maybe I have one question. I spend a lot of time working on driverless cars, and over 90% of driving is boring. And so we spend an enormous amount of time doing long-tail discovery and trying to address those last few percentages. So maybe a slightly more provocative version of Steve's question is like, are you solving boring problems?
I hope not. No. So I think that the problems that I'm solving are really, really inspired by these applications first, right? It's trying to figure out like places where robots are actually providing some epsilon utility to actually make, collaborating or doing something easier, right? For the stop motion example, like being able to kind of do these motions more reliably and scale that to, a bunch of different motions over time to kind of film this clip, that's something that I literally couldn't do alone, or at least not at the same quality. Now, there are parts of these tasks that I do think are boring, right? Like especially some of the more kind of semantic manipulation tasks that I hinted at with that future work direction. And I think we need to move away from that and start looking at these more realistic tasks.
I guess how can you codify that? Like there's nominal, there's off nominal, and then there's much further out. Like you have faith that the tasks that you looked at span that space?
Definitely it's not spanning that space yet. But I think we're definitely saturating on, the tasks that we've collected tons and tons of data for, especially like these claw machine style pick and place tasks, like with the toy kitchens.
I think, go ahead, Dieter, please.
On the sandbox kind of task. So the examples you showed there were, especially the teaching part, right? Like teach, like how to put it into that bag. So the actions are still pretty simple, right? You have a bounding box and then you say go to or something like that. But in settings like the one you show in the video or in general, often go to doesn't specify well enough what the robot should actually do, right? There's whether you want to put something into that paper bag, whether you want to pick up the paper bag, whether you want to close it. The actions are very, very different,
Yes.
right? And then also, I guess teaching those will become much harder because a person might not suddenly have to spend half an hour teaching it how to close a bag or something like that, right? Or even longer, right? And then also this notion of if you keep on doing that and you keep on adding actions and functions to your system with this proliferation, could there be a case at some point where people just totally lose overview of what's going on here or what the robot can actually do?
Yeah, so that's a fantastic, fantastic question. So first, to answer the first part of the question, right? So for this first Vocal Sandbox paper, the behaviors we limit ourselves to were very simple, like these programmatic, like hand-scripted primitives. And for the stop motion example, it was like actually learning like very simple, like dynamic movement primitives for like path following for the camera motions. Now, in kind of ongoing work, Jen is actually looking at different ways of expanding this policy class. And again, this gets to Abhishek's point about kind of this trade-off between like safety, transparency, and expressivity, right? So one way to kind of get at some more complicated motions is to start modeling like the actual affordances of the end effector relative to the object, right? This will handle things like, actually how we place things into a bag, kind of modeling all of SE3 in a more transparent way, just kind of showing like how the gripper is going to be oriented as we interact with different objects. Now for the second part of your question, which is how we kind of scale this system as we get more and more functions and arguments, the work on proactivity I mentioned is actually building directly on Vocal Sandbox. And it's kind of using the language model to kind of just say, okay, here are the different functions that I have access to. Here is like a handshake that I'm going to establish between the robot and the human, where the robot's going to ask the human questions about the task they're trying to accomplish. And the robot's then going to kind of take the burden of suggesting new actions or suggesting new things to do relative to the person's goal. So even as the space of functions of this library of things grow in the API, the hope is that the model can kind of do more and more of the work and kind of suggesting what the relevant behaviors are. So the person doesn't have to keep this mental model of like the whole library of things that are available.
Well, let's thank the speaker again, and thank you all for coming.